The universe is in perpetual motion. Planets orbit stars, galaxies spiral through the cosmos, and even at the smallest scales, atoms vibrate with ceaseless energy. Understanding this motion is fundamental to our comprehension of the universe. This is where the fascinating realm of rigid body mechanics comes into play. It provides the tools to analyze the motion of objects that don't deform as they move. Imagine a spinning top, a whirling dancer, or a rotating planet. These are all examples of rigid bodies in motion, their movements governed by a fascinating interplay of forces and inertia. Unlike linear motion, where an object moves along a straight path, rotational motion involves movement around an axis. This axis becomes the pivot point, dictating how the object spins, twirls, and rotates. The beauty of rigid body mechanics lies in its ability to simplify complex motions. By treating objects as rigid, we can disregard the complexities of internal vibrations and deformations. This simplification allows us to focus on the fundamental principles governing rotational motion. It's like studying the elegant waltz of a dancer without getting bogged down by the intricacies of their muscle movements. From the graceful pirouette of a figure skater to the intricate rotations of a gyroscope, rigid body mechanics unlocks the secrets behind these captivating movements. It provides the framework to understand how forces influence rotations, how mass distribution affects spinning objects, and how energy is conserved in a whirling world. So, let's embark on a journey to explore the captivating world of rotational motion, where objects dance and twirl, revealing the hidden order within the universe's perpetual motion. In the world of rotational motion, torque reigns supreme. It's the driving force behind every spin, turn, and twist. Just as force instigates linear motion, torque is the instigator of angular acceleration. Imagine trying to open a door. You don't push on the hinges, do you? No. You apply force at the handle as far from the hinges as possible. This force, multiplied by the perpendicular distance from the hinge, the pivot point, is what we call torque. Torque is the rotational equivalent of force, and it's all about creating a twisting or turning action. The greater the torque, the greater the angular acceleration it produces. This is why a longer wrench makes it easier to loosen a stubborn bolt. The increased distance from the pivot point amplifies the applied force, resulting in a larger torque. But torque isn't just about magnitude, it's also about direction. The direction of torque determines the direction of rotation. Imagine a clock face. A clockwise torque will cause an object to rotate clockwise, while a counterclockwise torque will result in counterclockwise rotation. Think of a playground merry-go-round. Pushing it tangentially at the edge generates the most torque, sending it spinning merrily. Push closer to the center and you need more force to achieve the same rotational speed. That's torque in action, illustrating how the interplay of force and distance dictates the dynamics of rotational motion. Just as objects at rest tend to stay at rest, rotating objects exhibit a similar reluctance to change their state of motion. This is where the concept of rotational equilibrium comes into play. When the net torque acting on an object is zero, it's said to be in rotational equilibrium. This doesn't necessarily mean the object is at rest, it simply implies that its rotational velocity remains constant. Imagine a balanced seesaw, with two children of equal weight sitting equidistant from the fulcrum. The torques they exert balance each other out, resulting in a state of rotational equilibrium. The seesaw remains horizontal, neither tilting towards one child nor the other. However, disrupt this balance and the seesaw tips. Add more weight to one side or move a child further from the fulcrum, and an unbalanced torque comes into play. This unbalanced torque will cause the seesaw to rotate, accelerating until a new equilibrium is reached. The same principle applies to all rotating objects. A spinning top remains upright because the torque due to gravity is balanced by the torque from the support force at the tip. Disrupt this balance, and the top begins to wobble and eventually falls. Understanding rotational equilibrium is crucial in fields like engineering and architecture, ensuring the stability of structures from towering skyscrapers to spinning gyroscopes. Section 4. Revving up. Equations of angular acceleration. Just as linear acceleration describes changes in linear velocity, angular acceleration quantifies changes in rotational velocity. It's the rate at which an object's angular velocity changes over time. When an unbalanced torque acts on an object, it doesn't just start spinning at a constant speed, it accelerates. The greater the torque, the faster the object's rotational speed changes. To understand this relationship, we turn to the equations of angular acceleration. These equations link angular acceleration alpha, torque, tau, and moment of inertia, I tau, equals I alpha. This equation tells us that the angular acceleration of an object is directly proportional to the net torque acting on it, and inversely proportional to its moment of inertia. Consider a figure skater performing a spin. As they pull their arms closer to their body, their moment of inertia decreases, causing their rotational speed to increase. This is because the angular momentum, a measure of an object's tendency to rotate, remains constant. To compensate for the decrease in moment of inertia, the angular velocity must increase, resulting in a faster spin. The equations of angular acceleration provide a powerful tool for analyzing and predicting rotational motion. From calculating the torque required to accelerate a spinning wheel to understanding the intricate movements of a gyroscope, these equations are fundamental to our understanding of the physical world. Section 5. The moment of inertia, a tale of mass distribution. Imagine spinning a bicycle wheel and then trying to stop it. You'll notice that it takes more effort to stop a wheel with its mass concentrated at the rim than one with its mass distributed closer to the axle. This resistance to changes in rotational motion is due to a property called the moment of inertia. The moment of inertia is the rotational equivalent of mass. Just as mass dictates an object's resistance to changes in linear motion, the moment of inertia quantifies an object's resistance to changes in rotational motion. The greater the moment of inertia, the harder it is to start, stop, or change the object's rotation. The moment of inertia depends not only on the object's mass, but also on how that mass is distributed relative to the axis of rotation. Mass concentrated farther from the axis of rotation contributes more to the moment of inertia than mass located closer to the axis. Think of a tightrope walker holding a long pole. The pole's large moment of inertia, due to its mass being distributed far from the axis of rotation, the walker's feet, makes it harder for the walker to rotate, thus increasing their stability. Understanding the moment of inertia is crucial in numerous applications, from designing efficient flywheels for energy storage to optimizing the performance of rotating machinery. It's a key concept that underscores how mass distribution plays a critical role in the dynamics of rotational motion.